Next, magnetic field patterns. Previously, we said that there is an invisible magnetic field surrounding a magnet. And if you place any magnetic material in this field, it will be pulled towards the magnet. We can visualize this field by performing an experiment. We place a bar magnet on a cardboard, sprinkle some iron filings on a paper, place it above the magnet, and tap the paper gently. The iron filings arrange themselves in patterns as shown here. These patterns indicate the magnetic field of the magnet. Because of this, we see that the iron filings arrange themselves in a specific pattern. This pattern also tells us a lot about the strength of the magnetic field. We see that more iron filings are gathered at the two poles of the bar magnet. This means that the field is stronger as you move closer to the poles. The field is weaker at the center. The field patterns differ depending on the shape of the magnet. Here is the field pattern for a horseshoe magnet. Again, we see that more iron filings are gathered at the poles. A magnetic field is represented graphically by lines of force. Mapping magnetic lines of force. Now, we fix a sheet of paper on a drawing board. Place a bar magnet on the sheet of paper and trace its boundary. Place a compass at the North Pole. The compass needle comes to rest in a particular direction. Mark the other end of the needle as shown here. Move the compass such that its south pole is where the North Pole was and mark the new position of its North Pole. Repeat this until you reach the other end of the magnet. Join the points with a smooth curved line. The curved line represents a magnetic field of force. Place the compass at different points near the North Pole and map the lines of force. Now let's see patterns due to two bar magnets placed with opposite poles facing each other. We place a paper sprinkled with iron filings above the two magnets and tap the paper gently. The iron filings distribute in a pattern like this one. This can also be represented diagrammatically. Next is patterns due to two magnets placed with like poles facing each other. Again, we place a paper with iron filings sprinkled over it above the two magnets. The iron filings distribute in this pattern, and we can also represent this pattern diagrammatically. In general, the magnetic field lines are close and continuous curves. Outside the magnet, the lines are directed from the North Pole of the magnet towards the South Pole, whereas within the magnet, they are directed in the exact reverse direction. The lines of force repel each other and they never intersect. And so in summary, magnets have a north and south pole. Around these poles are magnetic fields of force that extend out in all directions. These invisible magnetic lines of force leave the North Pole of the magnet, loop around, and enter the South Pole. The lines are more dense near the poles where the magnetic field is strongest. As you move away from the poles, the lines space out due to diminishing magnetic force. Two magnets will repel each other if like poles are facing each other. As you move like ends of two magnets near each other, they will be repelled. Notice how the lines bend as they impinge on the lines of the opposing magnet. If unlike poles are facing each other, the forces will attract one another. As you move the magnets close to each other, the lines of force join and condense, increasing the force of attraction. When unlike poles are lined up end to end, their combined forces create a unified magnetic field and behave as a single magnet.